Good afternoon, everyone. Today I'm going to talk balancing fairness and efficiency in tiered storage system with bottleneck-aware allocation. I'm a PhD student at Rice University. This work is done with my advisor, Professor Peter Varman, who is also at Rice University. So the multi-tier storage system with both solid-state drives and traditional hard disk are becoming more and more popular. It has several advantage over traditional flat storage in the data center, including improved performance for data access and reduced cost. Meanwhile, it also raises new challenges. One is how to provide resource allocation fairly among concurrent clients, and the other is how to maintain high efficiency for all devices. There's a large gap between SSD and a large speed gap between SSD and HD. It means that it's not viable to simply treat the storage system as a black box with a certain aggregate IOPS capacity. The system throughput is linked to access pattern of the application. It also depends on how the device capacity are actually divided between the applications. So this figure shows the architecture of the tier storage model used in this paper. The clients make requests to SSD and HD in certain ratio, and access to the SSD is referred to as a hit, and access to the HD is a miss. Please note that although we use hit and miss, it's not a cache architecture. The hit ratio of client is the fraction of our request to the SSD. The hit ratio is assumed to be relatively stable within an application phase. The scheduler dispatches the request from all clients to the storage array. The scheduler is aware of the target device or request, whether the request is go to disk or SSD. It contains two modules. One module is to monitoring the hit ratio of each client and periodically recompute the weights to clients based on our bottleneck-aware allocation algorithm. The second module is used to dispatch requests to storage array based on the relative weights. The storage is composed of SSD and HD arrays. The SSD and HD are independent devices without frequent data migration between them. In our model, we do not control the data migration and data placement. In a single type device, it's very easy to define fairness and achieve high efficiency. But in a tiered storage system with heterogeneous resources, if a client has different requirements on different resources, how should we define fairness? Another problem is efficiency. Actually, efficiency is a major concern for the service provider because it affects the resource consolidation ratio and the amount of the clients that it can serve at the same time. However, it's very hard to achieve both fairness and efficiency, high efficiency. Maintaining high overall system utilization might require favoring some clients while starving some others, which cause unfairness. On the other hand, allocation based on a rigid notion of fairness can result in low utilization because some clients might be unnecessarily throttled to maintain fairness. There's some existing solutions for quality service in our scheduling to mainly provide proportional sharing. Some of the work provide additional reservation and limits controls, but all of them are designed for a single resource allocation. There's a work called the Dominant Resource Fairness Model. We call it DRF, which proposed on NSDI 2011. This is designed for allocating multiple resource, but it does not explicitly address system utilization problem. Next, we will motivate our work with several examples. In a single device environment, suppose a single type of device, HD suppose, with a capacity of IOPS. The capacity of device is defined as its IOPS when continuously busy. If two clients sharing the device and they have equal weights, suppose the system is fully backlogged and it's working serving, with proportional sharing allocation, each of them will get 50%, which is 50 IOPS in this example. And the utilization of the device will be 100%. Actually, the device can be fully utilized for any allocation ratio. What if there are multiple resources? In this example, we examine the fairness in multiple devices. Suppose there are two devices, one is HD and the other one is SSD, with capacity 100 IOPS and 500 IOPS respectively. Please note this number is just some simple example to simplify the example. It can be any number. So if there are two clients with hit ratio 0.9 and 0.5, a client with hit ratio 0.9 means 90% of requests go to SSD and 10% go to disk. And similarly, if a hit ratio 0.5 means 50 requests go to SSD and 50 go to disk. So a natural extension of fair allocation will be applying proportional sharing to multiple devices. That is allocating the total IOPS in proportion to their weight. If you're using WFQ in this example, then each of them will get 167 IOPS. So if you look at the utilization, the HD is 100%, but the SSD is only 47%. So that means simply transferring WFQ to multiple resources will have efficiency problem. What happens if we try to maximize the system utilization? If we want to fully utilize the device, still the same configuration, the unique allocation are shown in this figure. That is, client 1 get 500 IOPS and client 2 get 100 IOPS. But now the problem is it fair? DRF, we already talking about DRF earlier. DRF is designed for multiple resource allocation. So how will DRF do? In DRF, a client's dominant resource is the resource that most heavily used by a client. So in this example, if client 1's hit ratio is 0.9, so the dominant resource are SSD, and for client 2, dominant resource are HD. So DRF will equalize the dominant share, and each of them will get 64% of the dominant resource. In this case, the utilization of SSD is 77%. So is DRF sufficient? The answer is no. Because DRF does not explicitly address efficiency problem. For example, if there's a third client with hit ratio 0.1, of course the dominant resource is HD, then each of them will get 39% of their dominant resource. In this case, the SSD utilization is only 48%. Actually, it will be worse if more clients bottlenecked on HD. So let's compare the two cases we just mentioned. The left figure shows the allocation for two clients with hit ratio 0.9 and 0.5. The right figure shows allocation when there's one more HD-bound client in the system. By comparing the allocation of the two cases, the allocation to client 1, which is the green part, reduced from 64% of the SSD to 39% of the SSD. And if you look at the utilization of the SSD, reduced from 77% to 48%. So DRF gets low utilization because it tries to equalize the dominant share for all resources without considering the system bottleneck. Next, we will introduce our bottleneck-aware allocation. We will call it BAA in the rest of the paper. We start from introducing a concept of fair share. In a single device, we could allocate equal IOPS to each client to get fairness. For multiple resources, instead of allocating equal IOPS, we allocate equal resource to each of the clients and see what IOPS they can get. So we define fair share of client and the IOPS it would get if each resource was partitioned equally among the clients. For example, suppose there are two devices with capacity 150 and 300 IOPS. There are three clients. Client 1 with hit ratio for nines, which means it has the requests go to HD and SSD in the ratio of 4:5. Client 2 has the same hit ratio, and client 3 has a hit ratio of 5:6. What's the fair share for each client? So this figure shows if each of them get 1/3 of each resource, the fair share of each client is shown in this figure. So the fair share for client 1 is non-IOPS, which means 50 from HD and 40 from SSD. And same for client 2. And client 3 got 120, which is 20 from HD and 100 from SSD. The fair allocation depends only on client's hit ratio and the capacity of the device. Actually, the fair share shows IOPS each client can get if equal resource, get equal resource and without resource sharing. When they share the system, we also want that. We want to keep this ratio. So now, then what's the fairness policy in tiered storage? We could use fair share and allocate IOPS in the ratio of fair shares, because fair share reflects what clients would get if running along with equal resources. But the problem is it might throttle some clients across devices, similar to the DRF example. So the solution is bottleneck-aware allocation by partitioning clients into different bottleneck sets and adjust the relative allocation based on the system bottleneck. Now we'll give some formal definition of bottleneck-aware allocation. We define a load balancing point equal to the capacity of SSD divided by the sum of capacity of SSD and HD. If a client has a hit ratio equal to this load balancing point, that means it has equal load on both devices and it can fully utilize both devices. If client's hit ratio is less or equal to this point, so its bottleneck is on HD and HD bound client and it belongs to HD bottleneck set, we denote it by capital D. Similarly, if a client has ratio higher than this point, it's an SSD bound client and belongs to SSD bottleneck set, denoted by S. Now we will define some fairness requirement by bottleneck-aware allocation. Some of them actually are already identified by some related work, and we'd also like to have those good properties. The first one is sharing incentive. It means no clients get less IOPS than it would get from equally partitioning each resource. The second one is MV freedom. Clients prefer their own allocation over the allocation of any other, so they won't envy others. The third one is a local fair share ratio. So that means the clients belongs to the same bottleneck set get IOPS in proportion to their fair shares. So what will be bottleneck-aware allocation do? So it will maximize the system throughput at the same time satisfy all the fairness requirement. Actually, this figure gives an idea how bottleneck-aware allocation guarantee fairness and maximize system throughput. So each of the circle denotes allocation that satisfy one of the fairness property. The green part denotes allocation that satisfy all the fairness property, and B will search the best throughput within this area. And you can see the DRF actually is at just one point in this area. So our method can have at least the same or better utilization than DRF. So now we will introduce how the fairness requirement are translated into concrete fairness constraints. We use two variables, ρD and ρS, to simplify the constraints. ρD and ρS are actually amplification factors to fair shares. We define ρD equals the allocation divided by the fair shares. Actually, it's very easy to find out that if ρD or ρS is larger than 1, that means the allocation is larger than its fair share. The first and the second constraints define all the clients in each bottleneck set get allocation in proportion to their fair shares. The third constraint is providing MV freedom constraints that no one get high allocation on all devices. So it seems to require n square of comparisons. We could simplify all the constraints to a two-variable linear problem. So the target function, the first one, target function is to maximize the system throughput. The equation 2 and 3 are capacity constraints, and the equation 4 are fairness constraints. So BAA will maximize the system throughput subject to all fairness properties. In our paper, we have a full section to prove that with this solution, we could satisfy all the fairness properties, including MV freedom and share incentive, and also local fair share ratio. And also, we could maximize the system throughput. Next, we will evaluate the performance of the bottleneck-aware allocation, which we will evaluate its performance BAA by both simulation and Linux system. The simulation is just mainly used to evaluate the behavior of the BAA. In the Linux system, we implement our prototype by interposing the bottleneck-aware allocation scheduler into the I/O path. We generally investigate the efficiency and fairness properties, including sharing incentive and MV freedom. The storage service used in this experiments include 1 terabyte Western Digital hard disk and 120 gigabytes Samsung SSD. So first, we will evaluate the efficiency of BAA. Suppose there are 2 devices with HD and SSD with capacity 100 and 5,000 IOPS. There are 2 clients with hit ratio 0.5 and 0.95 each. The left figure shows the total system throughput for WFQ, DRF, and BAA allocation. The right figure shows the SSD utilization. Because in this experiment, the HD utilization is always 100% for all the algorithms. We didn't show it. We just look at the SSD utilization. So we can see the WFQ get very low throughput and utilization because it tried to force all flows having the same allocation. DRF is better, but still is only 65%. Bottleneck-aware allocation get much higher utilization. But now suppose we have a third client with hit ratio 0.8. So we can see both the DRF and BAA utilization is reduced. And we should note that BAA does not always guarantee 100% utilization because if in this example, to get higher efficient utilization, you will violate the fairness properties like MV freedom. So actually, it's a trade-off fairness and efficiency. Subject to all the fairness constraints, this is the best utilization we can get. The second example, in this experiment, we will evaluate the dynamic behavior of bottleneck-aware allocation. When the system workload change, the relative in our implementation, the relative weights actually are periodically recomputed. In, like, for example, 1 second, we recompute the weights every 1 second. So in this example, suppose one client changes its hit ratio until 5-10 seconds. The system will have a low utilization for a short time, but the BA will pull back the utilization after recomputation the weight at time 600. So that means it will suppose the hit ratio is not accurate, so it might have a short time low utilization. But we could improve that by concurrent recomputation of the weights to improve that. In the Linux experiment, we first evaluate the efficiency of the bottleneck-aware allocation. In this example, there are 2 clients with hit ratio 0.3 and 0.95. So this figure shows the throughput for 3 schedulers. We can see the bottleneck-aware allocation achieve high system throughput, much higher than DRF or CFQ. And this figure shows, if you look at the device utilization, this figure shows the utilization for all the 3 algorithms. We can see B has high SSD utilization because it tries to maximize the system throughput. We should also know that SSD has much higher capacity and the increase of SSD utilization will increase the throughput a lot. The utilization, we should know that in BA, the utilization of HD is not 100%. We believe it is because the varying of the capacity and the change of the workload makes estimation not 100% accurate because we use a periodic recompute. We use a 100-second period to recompute the weights. So this could be further improved by more concurrent computation always, or we could use additional feedback solution to monitoring we could monitor the utilization, device utilization, and also the hit ratio change. Once we detect the change of the hit ratio, we could recompute immediately to improve that. Next, we will evaluate the fairness property of BAA, including sharing incentive and NV freedom. In this experiment, there are 4 clients. Client 1 and client 2 belongs to the D set, and the other client 3 and client 4 belongs to the S set. So this figure shows the fair share and throughput for each client. The first bar of each client shows the fair share amount in IOPS, and the second bar shows the IOPS each client actually get. So we could see every client receives at least its fair share, and the allocation are also in proportion to their fair shares. This figure shows the allocation on each device for the clients. So we try to see whether it's NV freedom. So we can see no one get high allocation on all devices. So for example, for the clients in D set, which is client 1 and client 2, it has a higher HD allocation. And for the clients in S set, that is client 3 and client 4, they have a high SSD allocation. So that means no one envies others' allocation, and NV freedom are guaranteed. Now we will conclude our work. In this paper, we proposed a model called Bottleneck-Aware allocation to balance fairness and efficiency. It has the fairness property of sharing incentive, NV freedom, and local fair share ratio. And subject to all those fairness properties, we maximize the system throughput. Now we are working on, there's some ongoing work. One of them is we are applying the bottleneck-aware allocation for broader multiple resource allocation, including CPU, memory, networks. And the another work we are working on is to define other fairness policy, including cost model, and also trying into some reservation and limits control for the clients. And another one possible future work is to implement a cache model in which the SSD is a cache of the HD. And of course, it will involve data migration between the devices and so on. That's it. Thanks. I'd like to take any question now.
Umesh Maheshwari from Nimble Storage. This is very interesting work.
Thanks.
In practice, the flash tier provides much higher IOPS than the disk tier, maybe 100 or 1,000 times more, right? Which means that unless the hit rate is over 99%, the system is going to be bottlenecked on disk.
Right.
And I was wondering if that kind of a dramatic ratio changes somehow the nature of this work.
Well, suppose it's for a single disk compared with SSD. Of course, it's most likely HD will be the bottleneck. But considering if you have a large HD array, so if the speed gap between those two are not so dramatically large, so we will very easily to have a balanced set clients on both sides.
Yeah, but if I could sort of extend the question, assuming that there was such a large difference between the two tiers, I'm wondering whether your model still holds, though, at least.
So suppose you mean suppose.
Yeah. Would you still sort of pursue this approach?
So you mean suppose the HD speed is much less than the SSD?
Yeah.
But even that, our work won't do worse than other work. And for that case, our work can get as the same with others. So So we won't do worse.
I see.
Yeah.
Got it. Okay, thank you.
Hi, good work. I'm switching from Data Storage Institute, Singapore. So we have some project similar to this kind of work. We call it QoS storage. And in that situation, we consider the fairness among distributed storage system. So I just want to ask, in your scheme, suppose it perfectly works for single node, but if the system is distributed node, means multiple nodes have all nodes have to schedule all the traffics. In this case, whether your scheme still can work.
Sarah, can you repeat the question?
I mean, your scheme is perfectly work for single scheduling, right? Just one scheduling. So suppose we have a distributed storage system which has multiple storage nodes. So the scheduling should be multiple schedule on each node. So in this case, how the scheme can work?
Yes, so currently we, in our experiments, we only for single devices, not distributed. But I think we could easily extend our work to multiple, to distributed system with coordination between, suppose we can use several schedulers and adding the coordination way to like balance. We could coordinate between the schedulers to balance the workload. Yeah, I think we could extend our work to distributed system.
Okay, thank you.
We could discuss it offline.
Yeah. Okay.
Kai Shen from University of Rochester. Interesting work. I also like the way that this can be formulated into a linear constraint programming problem, because then you can have efficient solution. What I wonder is that sort of just by chance, or have you seen possible optimization targets that would not turn into a linear constraint, so you don't have an efficient solution? Have you run into any nonlinear constraint when you were looking at a problem?
So I mean, this work is can be used to solve by the linear program. And is there any other problem that cannot be used by linear program?
I wonder, have you seen some other sort of optimization target, or maybe the constraints that are nonlinear, therefore you wouldn't have an easy solution like what you have in linear programming case?
To my knowledge, considering all the fairness constraints and requirement so far, we haven't found any. We could transfer all those constraints to this model using the linear program. Yeah.
All right. One other follow-up is that so formalizing all of those into optimization problem and solving it the way you did is very nice. When you apply this in practice, sometimes you have difficulty of getting certain input variables you need. For example, you have those fair share F variables and also the hit ratios. You did have little experiments sort of in Linux. Can you share with us some of the particularly challenging parameters to get as input to your optimization, like those F parameters and the hit ratios?
In the challenge, in the implementation.
You're acquiring those numbers because you need them as input to your optimization, right?
Optimization. I think the most challenging part is to accurately estimate the capacity of the system, because it might change from time to time, and you have to, in order to achieve high accuracy, you have to monitor the system closely and make changes based on the change of the system. So I think that's one of the challenge problem.
All right, thank you.
Thanks.